if I'm using the overall energy from the US, it gives me some one value. But if I'm looking at the local system, it gives me a different value. That's something we need to really figure out, something we need to, maybe we need to look deeper into the data and see what that data really represents and what it is. But it could also be true concept. So by that, what does that mean? People in Los Angeles use less energy, less power than people if you take the average in the US. So it means other places are using more power than the people in Los Angeles, essentially, isn't it? That's probably true. It is true. Essentially, if you look at the 1 million mark, which was in the 1800s, 1803 is when we hit the 1 billion population. And the thing is, it took almost 200,000 years when no humans really existed to 18. So it took about 200,000 years to really get to 1 billion. And it took only 200 years to get the rest, the additional 7 billion people. Okay, so it does really show you this big exponential growth happening in population in the last 200 years. So from 1803 to where we are right now, we went from 1 billion to 7.7 billion. The population is growing, as we saw it previously. It will continue to grow, and this is what their population growth is, and this is for the OAC. Look in that in parallel now with associated with primary energy. Now we talk about primary energy is excluding the conversion concept. So primary energy is, we're talking about the raw energy need of the people. We talk about the conversion issue later on. So for instance, if the wind is coming this way, and I make my blade parallel in the same direction as the wind, it's not going to capture any wind. Okay, that's how so we call it phasering. We change the blade direction to control how fast or how much we want to capture from the wind. So typically in this area, we just move our blade so we don't really react to wind until a point where we call it cut in wind speed comes in when we start generating power. Okay? Then along this, we also control it. We want to really get the maximum point. So this is what we call a power curve. So with the wind turbines, the modern wind turbines, I'm not talking the old wind turbines, just is a static blade which just rotates until the wind dies, so it does not have any control. The modern wind turbines, we have control how much speed we want, because it's an induction motor. We have other speed controls. We're going to talk about it also. But the main thing is really what we call phasering. By changing the blade direction, we can control the speed. As the speed of wind increases, we can adjust the blade direction to control how much power we want to get. And at some point, say, below him, between here and this, what is what we call it a constant power. So regardless where the speed of wind is going to be in this direction, I want to get the maximum output. So as you increase the diameter, look at the increase I get in power. Okay, I'm going from 225 kilowatts to 300, and just increasing from here to here, I got is really a magnitude of 10 from going from this diameter to this. I'm going from 225 kilowatts to 2,500 kilowatts. So if this is my wind turbine, okay, this is this associated area for that. So the larger I can make the thing, the more advantage I will get, isn't it? But one thing would happen is the larger I make it, I have to pick this radius, because in here I can make it, if this is my ground, I can have this turbine. But if I have this turbine, my ground has to be here. So I have to keep increasing the height of the turbine. the wind tower. And luckily, as we know from process here, from what we know from meteorological data, the higher you go in height, the better the wind is in the same wind turbine, in wind regime. So obviously, as we make the turbine size bigger, that is also helping us to push it up, because that's what we have to do. Then as we go higher, obviously the wind speed is better. Typically this going from here onward, today, a good portion, this is offshore wind application. And mostly here, and for most part here, and this is onshore application. But you can see here, but the key thing here is, when I am in here, I can put a lot of small wind turbines, versus here, I put a small number of them, okay? So is that relationship also. As we go higher, of course, we get in a lot more power, but how many of them I can have is smaller number of this. Now, this is tip speed. So for tip speed, this is 0, it starts at 0. So if we were to take that curve and do it in relation with the tip velocity as a tip speed, that's really what that curve looks like, something like this, okay? Now, there are some people try to do some clever design, pictorial here, to show the different type of winds, what is really some of the efficiencies we see, what does this curve look like. For instance, this is for the vertical turbine. Some people drew something like this. This is for 2 or 3 blade. This is what they are maximum. So now, given maximum speed capability for a generic wind, the different blade types have different characteristics within this large environment. We are not going to go try to do this. This maybe, there's exercise we could do, try to figure out if I have a 2 turbine, 2 blade or 3 blade, what is really their curve now. So you can go ahead, find what the curve is for the different type of turbines, and that gives you the general efficiency profile of the different turbine design. But we are not going to do that in here. I just want to introduce to you what the different efficiency capabilities are of this different wind designs.